The third and most useful, most powerful tool in the geoscientist toolbox is the seismic survey. This tool uses sound waves that allow petroleum geoscientists and petroleum engineers to interpret what is in the subsurface. Seismic surveys are made from sound waves that travel through the earth. Like the science used to understand gravity and magnetism, the technology for acquiring, processing, and interpreting seismic waves has been around for a long time. What makes seismic surveys so useful today and why we still use this technology is because powerful computer processing capabilities coupled with advanced software development allow us to record, pinpoint, and interpret with ever-increasing accuracy where oil and gas might accumulate. But how do we pinpoint the exact location that will maximize our chances of finding producible oil? To understand the fundamentals of seismic technology, we need to understand the basic scientific principles of sound waves. When you drop a rock into water, a wave is created. It spreads out in a circular pattern. This circular pattern is called the wave front. From the source, we draw a line that serves as a right angle to the wave. We call this hypothetical line a ray. It allows us to give direction to the wave front. If you are in the water, you can feel the motion of the wave as it spreads over and past you, and it causes you to move. Within this wave, the high is called the peak, and the bottom of the wave is called the trough. Natural waves are caused by natural forces on the earth. When you swim in the ocean or a big lake, you can see or feel the motion of the waves as they rush to shore. Just like water waves, we can create sound waves that behave similarly. Like I explained earlier, geoscientists use energy sources, or guns, to create sound waves that are shot down into the earth. These waves are then measured with receivers called geophones on land and hydrophones at sea. Here are some examples of graphs that have been created using data from these receivers. They basically allow us to visually illustrate the formations and rock types below. There are three types of seismic waves that are of principal interest to the geoscientists and the petroleum engineers. Here, we'll look at water waves to give us a better understanding of sound waves and how they work. The first wave is the P wave, or the compression wave. The second is the S wave, or shear wave, and the third wave is called the Rayleigh wave, or the surface wave. All three are used in seismic work. Let's look at them in closer detail. We'll start with the P wave, the compressional wave. Imagine you are the blue dot in this animation. Now notice, when the wave hits you, it pushes you forward and then back. Now, here is the S wave, or the shear wave. This wave is what you would experience on the ocean. The wave pushes you up and then down and then up. Measuring the relationship between the P wave and the S wave allows us to calculate the travel time of a sound wave. The third wave is the Rayleigh wave, or surface wave. In these waves, the energy travels along or near the surface. Again, let's look at these two blue dots. The two dots move up and down, but the dot nearest the surface feels more of the up and down movement. The measurement of the magnitude of this wave allows us to make corrections when hydrophones, or sound waves, in water are used. We use the properties of these waves to help us build seismic surveys. We measure the travel times of these waves as they bounce off the Earth's underground structures. Let's talk about what these waves illustrate. Sound waves are affected by four properties when they pass through air, fluid, or rock. Say that these are the properties that influence seismic wave propagation, or velocity. The first property that affects sound waves is the density, or mass divided by the volume. For example, we have already mentioned that sound passes through hard rock faster than soft rock. The second property is the elasticity of matter. With elasticity, matter returns to its original shape after being hit by a wave. Some of the energy is absorbed, but some of it is reflected back. Amazingly, rock is elastic. It will stretch or expand just like an elastic band, which after being stretched will return or snap back to its original shape. It is a rock's ability to return to its former shape that makes it elastic. When rock is hit with sound waves, the rock expands and then contracts. Instruments can measure this movement. For instance, hard rock, with tighter stacked atoms, a matrix or crystal, doesn't contract as much as soft rock. The third property that affects sound waves is porosity, or the amount of pore space in the rock. These pores, depending on their size, change the speed of sound waves. If there are big pores, sound waves will pass through slower than if the pores are small or if there are no pores at all. The fourth property that affects sound is the saturation or type of fluid in the pores. For instance, a sound wave passes through water at the fastest rate. It slows down somewhat in the presence of oil, and it slows even further in the presence of gas or air within the pores. All of these properties affect the way sound waves are recorded. By studying their variations, we can determine the density, the elasticity, the porosity, and fluid saturation in the structures below. Ultimately, they allow us to determine formation characteristics such as rock type, depth, and shape.